Okay, I'm into the recording mode also. Just 2 more minutes will wait. Only 20 people are in the classroom, and I'll start it. Just 2 minutes, not more than that. So again, I repeat till people join. The portion for your first I is the first 2 units from the syllabus copy. Okay, please make a note of it. The first 2 units from your syllabus copy. What did I do here? Okay, without wasting much time now, 24 people are there. I'll start it. Okay, so we are into the third unit of Unix system programming, which is Unix processes. So there we started with what exactly the process means, how exactly a main function works. Then we started with various ways of uh, process termination, where we studied two ways, usually normal way and abnormal way. Then again we studied normal way. There are three types. The one is return, exit, and underscore exit. And in abnormal way, there are two system calls, which is abort and signals. Okay. Then we studied about the set jump and long jump. We said how exactly a process jumps from one process to another process by set jump and long jump. Then we said about get R limit, set R limit. Yeah. So this unit is very easy. Then very important. We said about memory allocations at runtime. We know how a memory is allocated at the runtime by three functions, which we usually studied in data structures also, which is calloc, malloc, and realloc. Then again we studied about one more function known as alloca. We studied malloc and alloca. Both are same. They allocate memory, but malloc allocates from the heap segment, whereas alloca allocates from the stack segment. So whenever you use alloca function, we don't have to free the memory. That is what is known to us. Okay. Abhishek, you want to say something? Abhishek Loni, type something. Okay. Then we said about very important thing, memory layout of a C program. Usually know how a program runs now. But what exactly happens when a program is in running mode? How the memory is allocated for each program? See, there is a file. Whenever you run a file, it becomes a process. So now when you are running a program, how the process occurs, from which segments the memory is allocated. If you can refresh it, we had initially the text segment where all machine instructions are executed. Then we had initialize segment. As I said, whichever variables are declared globally. I can go back to this. I'll just show you here. There is the memory layout of a C program. We had it in the code. Yeah, here. We had text segment where all machine instructions are executed. That is the system instructions, the compiler, editor, and all. Then we have initialize segment. As I said, the variables which are initialized globally. I repeat, the variables which are initialized globally are stored in initialize segment. See, this program is given to you. See, before whichever you have the memory segments. See, this is before main. So this is initialized. So initialize read write, because the value of A can still be changed in the main program. So in initialize there are two segments, initialize read write and initialized read only. That is here, I give an example here. Constant int I equal to 5, which says that a variable I, which is constant throughout the program now, whose value will never change in the runtime. So those, for them, memory is allocated from the initialize segment, which is a initialized read. Please remember, this is not given in the textbook also. So I'm just highlighting more on this. Then we have uninitialized segment, the variables which are declared globally, only declared, not initialized. Please remember that. For that, memory is allocated from the uninitialized segment, which is BSS, block started with symbol segment, we call it as. And initially it is initialized to 0. See, whenever you declare a variable, it is initialized to 0 by the system. Then you assign the value. So all this is this int B, for which memory is coming from uninitialized segment. We have int An array I have defined data of 10. Again, it comes from uninitialized segment because it is just initialized, not declared. So it is declared, not initialized. Okay. So for that, it comes from uninitialized segment. Heap segment. Heap segment is one where runtime system call comes into picture when you want to allocate memory at runtime. System calls like malloc, calloc, realloc. If at all these functions are used in the program, for them, memory is allocated from the heap segment, which is this statement. Then we have stack segment, which is a runtime stack, right? The variables which are declared inside the main, for them, memory is allocated from the stack segment. Yeah, and there is something on top of that, which is a command line argument. So there are command line arguments or environment variables. For them, the memory is allocated from the topmost layer. So memory layout, please make sure that you don't tilt this diagram, okay? Actually, it always starts with the lower address and goes to the higher address. This is what we studied. Memory allocation, as I said, and we studied environment variables. Very important here. We can get environment variables. Environment variables are the one which tells me the structure of the system. These are already predefined in the system, and that we can get it by the variable env by passing a third argument to the main function. And again, I said there are three ways of getting environment list. One is by env, passing a third argument. Next is by environ variable, and third is by get env system call. Yeah, this is what we studied in this also. Then we said put cnv, set env, and unset. Put means we'll add a new environment variable. Set env will change the value of an existing environment variable, and unset removes the value. For this, again, we studied the programs also. That is what I'm talking here. Get env, put env. See, students, please remember these programs are not there in the textbooks. Maybe they are there, but they are very lengthier and difficult for you to understand. And my slides will help you understand it in a better way and easier way. You can still find the easiest way. I'm also happy for that. But this is what I thought it is the easiest program which I could tell you. Okay. Then we studied about goto. As I said, the problem with goto is it cannot jump across the functions. So for that, we go with set jump and long jump. We started this. We studied set jump and long jump, how it works. Then get our limit, set our limit. I told in the previous class how it works. Next, yeah. Now the next concept, Unix kernel support for process. Before going this, I'll just skip here now. Okay. So we studied probably the other day when I had some other work. Sir has continued this, Prashant sir. Unix kernel support for files he has conducted, right? So what it means there is, whenever there is a file being opened in the system, what exactly kernel does at the backend? What exactly kernel does at the backend? How the file is opened, how a file descriptor is assigned, how the file table is updated, how the reference count is initialized, how the reference count is updated, how the inodes are changed. All that we studied under Unix kernel support for files, which means that the minute you start opening a file till you close the file, there are various things going at the backend. That is what we studied in the support for files. Now, same way, what happens when there is a process in the system? What happens when there is a process running in the system? Now, what is a process? A file under execution, right? So assume now, before going to the theoretical part, I thought let me explain the diagram itself here. Now assume that this is an entire a process, okay? This is full a process here. The block diagram which I have shown is a process. So when you have a file with you, and when you're executing that file, simple example, let's take a C program itself. C program is a file for you now. But when you start executing the file, it becomes a process. So when a process is being executed by the system on your system, right? You have done that. You go to the prompt, cc filename.c, then you type /a.out. The minute you type /a.out, the file which you are given, like see example I'm talking, gcc or cc demo.c, a sample C program. So till that point it is a file itself. You press enter. Yeah, now the file is compiled, but still it is not in running mode. The minute you type /a.out, now the file demo.c becomes a process. Now it is executing. Simple. Let's again go back to the memory layout of a C program itself. See, we had written a sample code. A C program was there. So when you execute that C program, it becomes a process. Now we know how the memory is allocated, right? Because in memory layout of a C program, sir, you told about the segments, the various segments. Yes, we know. Now how kernel will respond to that? It's not only one program which is running in the system. Very true. In your system, there may be n number of programs running at the same time. Now at this point, how the kernel supports for all the processes in the system when they are in the running mode. Okay, this is a sample of only a single process being shown here. See, now this is a process. The one which I showed in the rectangle here, actually it should be in an oval shape. Okay, students, please remember this, because processes are always represented in oval shape or round shape. You studied in OS also, right? So this should be an oval shape. Now this is a process. So when a C program like this is under execution mode, what happens when the kernel is told here? So let me first explain this diagram only, then you'll understand the theoretical part. So when a process is being executed, kernel has to keep track which all processes are being executed in the system. So for that, there are n number of processes in the system which are being running all time. So kernel should keep track of all those processes. So to do that, kernel maintains a table at the system level which is called as process table. Now process table which will keep track of all the active processes in the system. Please remember all the active processes. Now what I mean by active processes here? There is a file. When file is in running mode, it becomes a process. So the minute it becomes a process, every process is a process ID. I told get PID will give me the process ID. So that process ID is maintained in a table by the kernel known as process table. So what is process table here now? It's a table maintained by the kernel which keeps tracks of all the active processes in the system. Yeah, I know now. Now what does the process table do then? And process table will have two pointers. Sorry, will have two pointers. One pointer. Assume that this is a process now here. Okay, this is a process here. So whenever there is a process table has two pointers from the process table. Like this, there may be n number of process students. Please remember, this is just an example for a single process. Like this, there may be more than one processes. Now for each process, the process table maintains two pointers. One pointer points to the pre-process region table. So this is all in the process only, okay? One points to the pre-process region table and one pointer points to the pre-process U area. This is called as U area. Please remember, if you want, I'll just put it here only, because you should not get confused here. I'll just show you now. This is that will do this. This is called as pre-process U area. I'll tell you what exactly it means now. Yeah, now it is clear. Whenever a process is under execution mode, kernel maintains a process table which keeps tracks of all the active processes in the system. And for each process table entry has two pointers. One points to the pre-process region table and one points to the pre-process U area. Now what is the pre-process U area? Pre-process U area is the area which is maintained in the process itself, which keeps tracks of the file descriptor of the table. That is, whenever a process is executed, it is assigned an integer value, which is called as a file descriptor. So what is a file descriptor of the process? In which current directory the process is running, and from which root directory the process is being executed. Just like a history of a process. All the history of a process is maintained in pre-process U area. So whenever a process is under run mode, it has its entry are made in the process table. So this process table Each entry in the process table has two pointers. See, in the examples, you can write in this way only. All the active processes in the systems are maintained in a table by the kernel known as process table. And each entry in the process table has two pointers. One points to the pre-process region table, one points to the pre-process U area. What is the pre-process U area? It's an area which keeps tracks of all the information of the process, just like the file descriptor of the process, the current directory of the process, and the root directory from which root directory it is working. And at the same time, it has pre-process region table. Now, what is the task of a pre-process region table? Please remember, in the memory layout of a C program, we said, yes, there is a text segment, data segment, and stack segment. Text segment keeps tracks of all the machine level instructions. Data segment keeps tracks of initialized and uninitialized segments. And stack segments keeps tracks of runtime stack. So what does the pre-process region do is, before sending the information to the kernel region table. Now, what does the kernel region table do? Kernel region table has fixed amount of memory segments, which is a text segment, data segment, and stack segment. So for each process which is running, before sending it to the respective data segment for memory allocation, the pre-process region refines it, just like a preparation. Yeah, just like a preparatory exams what we have, like before going the finals we give preparatory exams. Same way, process also maintains a pre-process region table. Here what it does, it itself initially segregates which information should go to the text segment, which information should go to the data segment, and which information should get from the stack segment. So from there again it maintains a pointer which points to the explicit segments here in the kernel region table. Now kernel region table keeps tracks of all the memory allocation segments. Kernel region table keeps tracks of all memory allocation tables. Kernel process table keeps tracks of all the active processes. So from here, what does the process do now? Assume that the C program which I gave as an input, it is in run mode. Now once it is running, its entry is made in the process table. So once its entry is made in the process table, it has two pointers. One points to the pre-process U area. U area is a segment of a process which maintains the description of the process, just like the file descriptor, the current directory in which it is executing, and who is the root directory. At the same time, it has another pointer which points to the pre-process region table. Now, pre-process region table is a table which in turn later points to the kernel region table. But before pointing to the kernel region table, pre-process region table segregates the information into the various segments. Just like if the program has machine level instructions, for that the memory should be allocated from the text segment. If it has instructions from the initialized segment, it should be allocated from the data segment. If it is in the main program, it should be allocated from the stack segment. Like this is first pre-processed. So after pre-processing, again it has a pointer which points to the kernel region table. Now kernel region table is a segment which maintains the various memory segments, just like a stack, data, and text segment. So after this, each instructions, it points to the various segments, and for that specific instruction, it allocates memory from the segments which is given in the block here. That is, if there is a stack segment, that is, if there are variables in the main, it allocates from this segment, maybe the first. So again from here, it allocates the memory to the stack segment. So this is how your kernel maintains the information when a process is under run mode. Okay, is this clear? So once the process completes its execution, that is ./a.out you done, and you completed. Again, now this entry from the process table is removed. The pointer which was pointing is deallocated. This pointer is deallocated. This pointer is deallocated. And at the same time, the memory which was allocated is again deallocated. So this keeps on happening for each process. Yeah, is this clear? Unix kernel support for process. You understood how exactly happens? Please remember, when a file is under run mode, it becomes a process. So whenever there are n number of processes running, all process entries are made in a table by the kernel known as process table. process table. So process table keeps tracks of all the active processes in the system. And for each process entry in the process table, it has two pointers. One pointer points to the pre-process U area. Now, U area is a segment in the memory which keeps tracks of the file descriptor of the process, current directory from where it is being executed, and who is the root. And it points to another segment which is nothing but pre-process region table. Now, the task of a pre-process region table is to pre-process it, as the word itself says, pre-process. That is, before allocating it to the memory, you pre-process, you segregate it. Which part of the instruction should go to which segment of the memory. After that, it again contains a pointer to the kernel region table. Now, kernel region table is a segment which keeps tracks of all the memory segment in the system. The memory segment like text, all the machine level instructions, the memory is allocated from the text segment. All the initialized and uninitialized data before the main, for them the memory is allocated from the data segment. And all the runtime variables which are given in the main, for them the memory is allocated from the stack segment. So all these segments are maintained by kernel region table. Since the memory is strict in Unix, so only you get all time the segmentation fault error. Remember, I guess I had told once in your first sem also about this. Segmentation fault, why? Because memory is very strict in Unix. You can't play with the memory. Just like what happens in Windows. You get garbage will and all, but in Unix you never. You get segmentation fault. Why? Because memory is very strict. It should allocate from that segment only. You can't play with the segments here. Okay? So this is what happens for a single process. Now assume the C program which was executing completed its execution. What next now? Once the process completes its execution, its entry is removed from the process table. So once this entry is removed, the pre-process region entry is also removed for that. Similarly, this entry is removed. So once it is deallocated, the kernel region table also deallocates the memory which is allocated for this process. Again, this is deallocated. Okay, this is what is explained theoretically here now. See, every kernel has a process table that keeps tracks of all active processes present in the system. Some of the process belongs to kernel and called as system process. Yeah, there is, as I said, there are user process and kernel processes. So every entry in the process table, what I explained is theoretically given here. That's it. Every entry in the process table contains a pointer to the text, data, and stack segment, and pre-process U area. Now, what is a U area? It is nothing but an extension of process table that contains other specific data of the process, because process table only maintains the process ID, other information of the process like the process file descriptor, current working directory, root directory, inode number, and all those are maintained in pre-process U area. And all the process in Unix system except the process that is created by system boot are created by fork system call. Okay, these are all created, fork are called by fork system call. Rest all are the process which you make them run. That is what explained in this diagram here. Okay, clear with this? In the chat box for me. Okay, Abhishek, no issues. Is this clear? Unix kernel support for a process. What happens here? So when your file is under run mode, it becomes a process. Okay. Again, a request for you all, please don't get confused here, okay? Because you have kernel support for files as well as you have kernel support for process. So in the exams, you should not get confused of writing for process, files, and also please make sure that it gives you. The pre-process region table gives instruction to the kernel to place data in particular memory. It doesn't give instructions, Abhishek. It segregates it, and certainly it goes to that area itself. Just like I'll give an example of this, Abhishek. When you came to college for the very first day, right? You were not knowing where is CS department was. So at the main gate, there was a board over there, right? CS department to the D building. That is a pre-process region. So when you come to D building, then you find your classrooms here, Abhishek. Is this clear? See, what is the pre-process region? The very first day when you came to college here, you are not at all knowing where is CS department, mechanical department, and all. So the board initially at the college level, at the entrance, is a pre-process. They have pre-processed it. A block, administrative block. B block is mechanical building. C block is architecture building. D block is our CS department. So there they are segregated. That is a pre-process. It will not give instructions. It will divert it. Memory is fixed. So from there you directly came to D block, which is the CS department, and here you found your classrooms. Right? So fifth sem classrooms are in D block. Yeah, getting this example, Abhishek. Yeah. See, relate this to real-time examples. Pre-process region is the very first board which is put at the entrance of the college there. Main building, Ganesha temple and all. That is a pre-process. So once you come to D block here, again you have various classrooms. So you have to go in a specific classroom. That is a kernel region table. See, how can we relate with the real-time example of what technically we are studying here? Okay. I hope this is clear, everyone. Okay. Just moving ahead of this now. Now, this is what I told here. Same thing is explained theoretically also. See, a text segment is a segment of a process in which machine executable instructions code format. The compiler, assembler, text editor, all those instructions, memory is given from the text segment. Data segment, static and global variables in machine executable format. Stack segment, function arguments, automatic variables, and all at the runtime. And U area, as I said, it's an extension of the process table which keeps tracks of process specific data structure. Okay, this wasn't related to a single process. Matlab, एक process is running in your system. I got this information for a single process. Now, what might happen when in a process you create a process? We studied fork system called the race condition. So what will happen when a process will create a process in turn? Okay, so this is what we are studying. We'll be studying here. Now, in a process, assume that a process creates one more process. I'll just keep this aside here. I'll just hide this so that it is visible for you. So what happens now when a process creates one more process? Yeah, just like a fork system call, as I said. So for that also, forget about this writing part. Okay, listen to my instructions. So whenever a parent creates a child process, again the child process has this entry in the process table because I wrote a C program. So in C program, again I had called a system called fork. Now what is happening? The process which is running, in that again you are running a process. So parent and child. So if you create a process within a process, what happens? This is just an example for a single process, students. Please remember, like that, there may be n number of processes in the system. So now we are targeting, we studied here what happens for a single process. See, this is for a single process. This is for a single process. Now again, if there is more than one process in the system, again there will be 2 pointers here, one pointing somewhere, one pointing here. Again the same and so on. This is for a single process. Now we are studying what happens when a process creates a child process. So again, look at the diagram here. So as we know, or as Sir you told us, whenever a process creates a child process, all the process entries are made in the process table. Now assume that this is a parent which created a child. Now again there is a child process. Again his entry should be made in the process table. Now process table will have 2 entries. One is the parent, the main which I am running, and child which is created by the parent. Now for each process explicitly, again we have, this is a process. Again we have separately, we have pre-process region table, we have pre-process U area. For child also, we have pre-process U area, pre-process region table. Again the region table will points to the kernel region table. In turn, apart from that, again the parent process will maintain a file table which keeps tracks of which files are being accessed by the parent and child. Only that is the extension here. Because parent and child, every process has its separate U area and pre-process region. Child also has pre-process region and pre-process U area. And again this pre-process U area will in turn will point to the kernel region table. Now again if you look at the kernel region table, every process has its own instructions to be executed, right? So in a parent process there may be some globally assigned variables and all. So for all such variables, you have a separate segment given from the stack segment. So the stack segment is different for parent. At the same time, the stack segment is different for the child because they are executing in their own region. Similarly, for parent, there is a separate data segment from the kernel, and for the child, there is a separate data segment. But if you look at this, there will be only one text segment for all the processes. There will be only one text segment. So now why one text segment? Because text segment is a segment which contains machine level instructions, which maintains only a single copy of the compiler, editor or assembler. So When only there is a single copy, for all that memory is allocated from the single text segment. Please remember this. So whenever there are n number of processes, there will be only a single text segment, but where there will be n number of stack and data segment depending upon the requirement of the parent and child. And in turn from that, they also maintains a file table. Now file table is a table which keeps tracks of all the file opened by the parent and child. This is just an extension, just to keep a record, where we are keeping the record like which all the files are opened by parents and which all the files are opened by child. Now this block diagram shows a parent-child relationship for a single parent and child. Similar lines, if there are more than one child, again for this child, you will have a file table separately, you have a preprocess URL separately. Again for that child, you may have a stack segment different, you may have data segment different. But for all them, there will be only one text segment maintained in the system. So please make sure in the exams what they're asking you, whether they're asking you kernel support for a single process or kernel support for parent-child relationship. If at all they ask like parent-child relationship, this is the block diagram which you should draw it, this one. And if they ask for a single process, this is the block diagram which you should draw it. Okay. So in that, when you are working with the parent-child now, okay, I mean you're working with the parent-child, there are some attributes which are inherited by the parent only. Now, as I told you here now, see, there is a parent and there is a child process. But at that time, there are some attributes which are inherited from the parent itself. And now, which are those? So when you have more than one process, that is a parent creating a child process, they can either inherit their own attributes. Now, which are those attributes? Current directory, because a child process running from the parent itself. So the current directory is the attribute which is inherited from the parent. The root directory, again because parent and child are running from the same root directory. Signal handling, this is the concept which we'll take in the next unit. But right now just understand that signal handling is like any unavoidable interrupts. Okay, those are given for parent if it is given. Same thing goes for the child also. Signal mask, if a parent has to be protected, same way the child also has to be protected. It is inherited. You have U mask. U mask is nothing but the process default permission. See, as you know now, when a process runs, whenever a file is created, you have default file permissions, right? 666 or 444, whatever it is. So that is called as U mask. So whatever the U mask parent has, if parent has read, write, and execute permission, the child which it has created will also have read, write, and execute permission only. Okay. Controlling terminal, there is again nice value which is called as a priority value. If parent has a priority to be executed, at the same time its child also has the same priority. The next one is controlling terminal. From which terminal you are running, the child also runs from the same terminal. So these are the attributes which are inherited from the parent when a child is running. Now on the same lines, which are the attributes which are different for parent and child? So whenever a parent and child is executing, there are some attributes which are common and there are some attributes which are different. Please remember, in the exams, they can twist you. Explain the kernel support or explain the data structure for parent-child relationship of a process. If they say this is the block diagram you should draw. Again, they may extend the question like asking, explain the attributes which are common and different for a parent-child. So these are the attributes which are common and these are the attributes which are different. Now, which are different? Process ID, PID. As I said, just like every file has a unique number, every process will have a ID called as process ID. So parent will have a different ID. At the same time, child also has a different ID. We saw in that example, see, get PID and get PPID. Both values were different. Why they were different? Because every process gets a new ID. So this is the attribute which is different for parent and child. Again, there is a parent process identification. So child and parent both will have their different IDs. Again, this child may create a child process. So at that time, this becomes parent and the new process which is created becomes a child. So these are the attributes which are different. There is something known as pending signals. The signals that are pending delivered to the parent process. Now, what I mean by this pending signals. Now, parent could have got some instructions At the same time, child also will get some instructions, but not the child has to follow the instructions. Pending signals, I'll give a simple example here. We'll get a message from our higher authority saying that by Friday, every student of yours should submit the assignment for us. So I'm getting the instructions that by Friday, everybody should submit the assignment. Now I'll again put a question to you saying that by Friday, you should submit me the assignment. But never happens. People never submit on time. So whatever the signals I'm getting will be always differing from parent and child process. So if a child is given a signal to stop, a child may not stop because it's in a run mode. So the signals what are got for the parent and for the child may be different also. This is what more of this detail will tell in the later when I come to the next unit. So at right now you just remember pending signals are the signals which are given to parent process. So those are executed differently for parent and child. There is alarm clock time. Again, the alarm clock time is reset to 0 in the child process. So when a parent starts, the alarm starts working. When a child starts, again it will start from the 0 because child started after parent, right? So both of them also will have different alarm timings at the system level. And there is file lock. The lock which is set by parent is not inherited by the child. Now child can have its own locking mechanism. That is, we studied in the file and record locking. So these are the various attributes which are different for parent and child. Please remember this. More of this I'll take in the next unit, okay? Because this is a detailed concept to be told for you. Yeah. So is this clear, everyone now? So probably this completes your third unit, which I took 9 classes, I guess, to complete this. So the overall snapshot of the third unit is this. We started with the main function. We know, sir, what is a main. A bootstrap loader runs at the runtime. Every time a memory's address is given to that initially, then your program starts execution. Then we said a command and argument, which is argc and argv. Then we said about process termination. Process termination, we have normal and abnormal termination. Environment list we studied. Environment variables we studied. Here we get 3 functions: env, environ, and getenv. Environment variables, again we have get env, put env, set env, unset env. Memory layout of a C program, the layer right from text, data, that is initialized, uninitialized, heap segment, stack segment, and command and arguments. Then memory allocation, malloc, calloc, realloc, and alloca. Set jump and long jump is the extension of goto and label, which can jump across the functions, which I gave an example. Set R limit and get R limit. You can know which are the resources are given to your system, how the values are assigned, what are the maximum values, how the values can be changed. It has a structure which will give the value of a current limit value and the maximum limit value. Then we said about kernel support for process. Now see, this becomes a pre-process region. Abhishek, again I can give an example here. This becomes a pre-process region table. More of environment variables or more of memory layout is in that concept. So that becomes a region table then. Okay. This completes your unit 3 from the syllabus. Why there are 2 file segments in the file table of parent child? Every process has a different file segment, right, Abhishek? Abhishek, I hope this is, you're talking about, every process has a different file segment, Abhishek, because parent maintains a parent ID as well as child, because this is a parent entry, this is a child entry. Parent has its entry in the file table, child is pointing to the parent from which it is inherited. Parent, child is pointing to its file, parent is responding to this child process. Parent also should know which files child has opened, child also should know which file parent has opened. So it's a vice versa. Parent should know what child is doing, child should know what parent is doing. So these are 2 pointers over there. Is that clear, everyone, students? Obviously, Abhishek, both are pointing to the same file segment because you are running a parent and child from the same file, right, Abhishek? I hope this is clear. Yeah, please look into the format also properly, Abhishek, because as I said initially, parent inherits a child. So when parent inherits a child, both are in the same file segment. Okay. So probably next class, your Girish sir will continue, okay? Because again, to start the next unit, I will want 2 different classes. So Girish sir will continue. the next class. Okay, so please give your attendance over here for me. The PPT as well as the notes I'll share with you once I'm done by the end of the day. Okay, anybody can please confirm me these questions, okay, whether they are the previous one or the new one. I'll also just try it out. Let me check. Yeah, this is correct one. You want me to answer this? Yeah. Okay. This is the correct one. Okay. So this completes your unit 3 from the syllabus. Yes, Varun, I'll give you. You are all waiting for that. I'll do it. Once the unit gets over, I'll give that. Okay. Probably by tomorrow, I'll send it. And one more thing, students, please remember, tomorrow I won't be taking the class for you, okay? Because I'm having a supervision duty. So probably my next class starts on Monday itself, Tuesday or Monday. Let's see on the timetable. So please make a note of it. Varun, if any other faculty wants it, you can just tell them, okay? My tomorrow's class, if anybody's portion is remaining, you can always convey them. Okay, fine. Oh, this is clear. Yeah. My PPT, I'll one thing again, the PPTs, videos, and all, we are sharing the Google Classroom only. See, Prashant sir has again shared one more link. There are 3 links which you have for separate your classrooms, and there is one more link which is for the entire notes and all. So all the things we're dumping there only. So please join that room also. Okay, I'll share the code with you for joining that. If you have all, because few people are already there in the classroom, so make sure that you join there. Okay. So note, next class is taken by Girish sir at 11 o'clock, and tomorrow's class, Varun, please adjust with somebody. Okay. Yeah, I'll stop it. Thank you. Have a nice day, everyone. Bye.